So in the next set of videos, we are going to talk extensively about thermodynamics, and this is really going to be a big chunk in physical chemistry, and we'll spend a whole lot of time covering a variety of concepts, trying to get some intuition of why certain laws in thermodynamics are in place, and also solve a whole bunch of practical problems so you get a hang of how thermodynamics plays a major role in our day-to-day lives. So thermodynamics, if you look at the origin of the word thermodynamics, basically thermo means heat in Greek, and dynamic actually means power or strength. So thermodynamics is basically a study of relationships, interrelationships between heat, work, and energy. So interrelationships between heat, work, and energy. So when we look at these, you'll begin to appreciate, these two quantities, heat and work, are not two entirely different, entirely separate entities, but they are in fact equivalent to each other, and how they bring about change in the energy content in a body or in a system. So it's all about these interrelationships. In our day-to-day lives, we're actually surrounded by processes, and many machines and devices of modern day living involve these interconversions between heat and work. For example, if you look at an automobile engine, your car engine or a bus engine, it's basically a device that converts heat to work. And when you're dealing with processes that actually involve chemical reactions, where let's say chemical energy, basically the energy stored in the chemical bonds in the reactants, when that chemical energy is converted to heat energy, like for example you're burning a fuel, now this heat energy can then be used to do some mechanical work, like just what happens in an automobile engine. So whenever you have processes that involve chemical reactions and you're looking at energy conversions and their interrelationships, their thermodynamics is often referred to as chemical thermodynamics. So this branch of thermodynamics basically deals with energy interconversions and chemical reactions, and it gives us a lot of information about these chemical reactions at equilibrium. So first of all, this can tell us if a particular reaction will happen or not. Let's say you have two reactants, A plus B, giving rise to C. So it'll basically tell us if this particular reaction is energetically feasible or not. If you combine these two reactants, is the reaction going to be spontaneous, or do you need to supply some energy for this reaction to occur? First of all, whether this reaction is possible, whether this reaction is possible or not. Spontaneity, energetically feasible or not. So if a reaction does occur in a particular direction, let's say this reaction goes spontaneously and A plus B giving rise to C, it'll also tell us, dynamics also gives us an idea of how far this reaction will proceed. Will this reaction proceed to completion, meaning the entire reactants here go completely to C, or do they come to an equilibrium where some of the reactants are remaining and they are in equilibrium with the products? How far will a reaction proceed? How far will a reaction proceed in a given direction? Thermodynamics can also give us some insight on what drives a chemical reaction. So, what is the driving force behind a chemical reaction? Driving force behind a chemical reaction. So besides these, it can also help us predict how much heat will be evolved in this reaction, how much heat will be evolved, or let's say absorbed, in in this reaction. So you can also have thermodynamic processes that are just physical processes that don't necessarily involve any chemical reactions, but just processes like phase transformations. For example, a liquid going into a solid, melting or freezing or boiling. So thermodynamics will tell us at what point, for example, will these liquid and solid phases of that material, let's say if you're talking about water, then it will be water and ice, when do they exist in equilibrium? At what temperature will water freeze into becoming ice under normal conditions, and when will water boil, and things like that. Or it can also help us predict how difficult is a phase transformation. For example, if you're looking at converting graphite into diamond or diamond into graphite, thermodynamics will help us predict what sort of conditions are required to convert one phase to the other. So these are, again, remember, these are physical changes. This is not a chemical reaction. It's actually just a physical change where you change the way atoms are arranged in a particular material. So, and that transformation occurs under certain conditions which thermodynamics will help us to predict. We'll also talk about various laws of thermodynamics, which again apply only when a system is in equilibrium or moves from one equilibrium state to the other. So when we say, thermodynamics is a study of interrelationships between heat, work, and energy, we mean these relationships when the system is at equilibrium. System is at equilibrium. So that is the key here, and you will be able to appreciate this part better when you go through the subsequent videos. So when we talk about laws of thermodynamics, they only apply when the system is in equilibrium or when it moves from one equilibrium state to the other. So they don't apply to any transients or any pathways that the system takes to go from one state to the other, and how and at what rate these energy transformations occur. For example, chemical thermodynamics doesn't tell us anything about how fast a reaction will occur. It will only tell you whether the reaction will occur or not, how much energy will it, how much heat will it generate, and what is the driving force, and so on. But it will never tell you, how fast, what is the rate. So for that you need to go to chemical kinetics. And all these terms like system and state and etc. will make more sense after the next few videos. So stay tuned.